Now that we understand what the cross product is and how to compute it, let's try to understand the cross product geometrically, or learn what we can use or how we can apply the cross product here. So let's say we have two vectors, u and v. And remember, this is specifically for n equals 3. So our ambient space is R3 here. These two vectors determine a parallelogram. So if you were to take a copy of u at the end of v and a copy of v at the end of u, what we would have is a parallelogram in two-dimensional space, right? So here's a parallelogram. Sitting inside R2. And so since we understand vectors and we also understand shapes pretty well, we should be able to relate our knowledge of shapes to our knowledge of vectors. And so one of the first things we could ask ourselves is, what is the area of this parallelogram? So let's call this parallelogram capital P. So what's the area here? Well, the area in general of a parallelogram with base length A, side length B is just AB, right? Excuse me, AB sine theta, where theta is this angle here. And so if we have that the sides of this parallelogram are actually vectors, well, then we can understand the side lengths as the magnitude of these vectors. And so what we get here, let's look back at our original picture. What we get is that the area is equal to the magnitude of u times, so this is the base, right? And then times the height. And what's the height? Well, in the abstract case, it was b sine theta, but now for us, b, or this length here, is going to be the magnitude of v sine theta. And so the area of this parallelogram is given purely in terms of understanding these two vectors that determine this parallelogram. And it turns out we have this important theorem that the magnitude of the cross product u cross v is equal to magnitude of u, magnitude of v sine theta. And so really, the area of this parallelogram determined by vectors u and v is just the magnitude of the cross product of the two vectors. And if you'll remember, in the properties that we discussed here, I said we'd come back to this specific property that u cross u, if you take the cross product of a vector with itself, you always get 0. Well, this makes sense when you're interpreting the cross product or the magnitude of the cross product via area, right? Well, if you take the cross product of u with itself, so here's u, and then you have another copy of u. Well, what's the area of the parallelogram that's spanned by these vectors? Well, it's 0, right? Because they overlap. And so this makes sense geometrically as well. So let's do an example here of how we can use the magnitude of the cross product to understand area. So here's an example. Let's say we have a triangle T with, this is a triangle with vertices 1, 2, 3, 0, 2, 5, and 5, 1, 2. And we want to ask, what is the area of this triangle? Well, given two vectors, we know how to compute the area of a parallelogram, but in this example, we don't have any of that, right? Instead of two vectors, we have 3 points. And instead of a parallelogram, we have a triangle. So how could we use these notions that we've just discussed to solve this problem? Well, if you know 3 points, you also know 2 vectors, right? So let's say we have the points 1, 2, 3, and this isn't geometrically accurate, but it's still a schematic to understand what's going on. We have 0, 2, 5, and then 5, 1, 2, right? And so if we know 3 points, we also know 2 vectors. Or in fact, we know more vectors than that, but we know at least 2 vectors, right? Because we know how to compute the vector or a vector between 2 points. So if we call the vector 1, 2, 3, P, the vector or the point 0, 2, 5, Q, and the point 5, 1, 2, R, well, we know how to compute a vector between 2 points, right? Let's call this vector PQ. And we have another vector PR. Cool. So now we've resolved the problem that instead of 2 vectors, we have 3 points. Well, we've learned that if you're given 3 points, you have 2 vectors kind of implicitly. But now how do we handle this triangle here? When we know, well, if we took a copy of PQ here at the end of PR and a copy of PR at the end of PQ, we would have a parallelogram. Well, we would know how to compute the area of this parallelogram, but how would we compute the area of a triangle? Well, if you intersect this parallelogram diagonally with a line that passes through the points 1, 2, 3, and 5, 1, 2, what you've done is you've now realized a parallelogram as the juxtaposition of 2 triangles, right? And the area or the triangle that we want the area of is one of these 2 triangles that was the result of splitting your parallelogram. So this would be T, right? And so what does that mean? Well, that means that the area of T is 1/2 the area of the parallelogram P. So really, to find the area of this triangle, we need 1/2 times the magnitude of the cross product PQ cross PR, right? Because we learned that the magnitude of this cross product would give us the area of that parallelogram. And to be more explicit, this would be 1/2 times the magnitude of PQ, magnitude PR times sine theta, right? Well, and now we want to understand, or we want to determine which one is more convenient in this context, right? And the indication comes down to this sine theta factor in the last formula here, right? We don't know what theta is in this context. And so we would have to go through a lot of extra steps to solve for it. So instead, we'll use this first one here, right? But I wrote both of these down to emphasize that depending on the context, one description of the area can be more convenient or better for a given context than the other, right? And so here, since we don't have an angle theta, let's just compute the cross product and then take a magnitude. So let's do this. So we need PQ cross PR. So let's find PQ and PR first. Let's give myself some room. There's PQ, here's PR. So PQ is going to be 0 minus 1. So that'll be -1 here. And for the sake of time, we have -1, 0, 2. And then PR should be 4, -1, -1, right? And now we need the cross product of these 2 vectors. So we need -1, 0, 2 cross 4, -1, -1, which is going to be the determinant of the 3 by 3 matrix I hat, j hat, k hat, -1, 0, 2, 4, -1, -1, which is 0 minus -2 for the first component. For the second component, we're going to have -1 times -1, which is +1. So we'll have 1 minus 8. And then for the third component, looks like we're going to have 1 minus 0, which is the vector 2, 7, 1. Cool. And so now we can take the magnitude of this rather easily. Magnitude PQ cross PR is given by root, and I'll go ahead and square these. So we have 4 plus 49 plus 1, which is root 50, whoops, root 54. And so if we know that the area of the triangle is 1/2 the area of the parallelogram, and we've just learned that the area of the parallelogram, right, this is area parallelogram, well, then the area of the triangle is 1/2 root 54, which is 1/2 root 9 times 6, which is 3/2 root 6. Okay, and so we can use this to compute the area of a triangle. Okay, so I think I'm actually going to break this video again into a third video and spend the third video on an application of the cross products, which is called the box product. And so we'll understand what the box product is and what it's computing in the next video.